Hello everyone. Hello everyone. This video I'm going to show you the integration. Okay, integration of power function. Okay, an integration of power function. I think the text will give you a rule like this. Okay, to a power function, the integration to a power function. We're doing integration with respect to x, and you have the range x1 integrate from x1 to x2 and give you this formula. And in this video, I'm just show you we can we can prove we can kind of I think that's not prove, it's just demonstrate the original idea of integration. And an original idea of integration is to find area under the curve. And I use this example, okay, and I use a function x squared. And now I'm trying to find the area under the curve between 1 and 2 and using the integration. Of course, if we apply this formula, we can get answer easily. But this video, I want to show the origin of the real origin of doing the integration. Okay, like I say, the area under the curve. Okay, what we want to do this to find the area under the curve of x squared between 1 and 2. We want to find find the area under the curve, and which is x2 x squared, and between BTWE and 1 and 2. Okay, so how do we do this? Find the area on the curve, and we just find the area. So we just slice in this area by many of rectangular patch. Okay, well, so what's that? So we can slice this here. For example, if I choose a point here, we choose the okay. Right now we'll use right end terminal. Right end terminal. Let me check. Is right end terminal? It's called right. Oh, it's called right end point. Okay, suppose I do the point here. Okay, right end point here, and I can, and this corresponding to the it's called xi, and it's corresponding to the f of xi. And so if I apply this also here, okay, here, if I select a point right of the okay xi, and this area is this area is called delta x. Okay, so the area under the green curve, green curve will be f of xi times delta x. Okay, and we will later show what delta x is. And I keep doing this. I also keep doing this with, for example, we use here. We can also slice this. Okay, this going, and we keep the same amount of delta x. This would be like this. This also some xi here, and this also corresponding to the another f of xi. And we just keep doing this. We can slide the area between the 1 and 2, and by lots of this rectangular very small rectangular area, and we keep adding them together, and then we will find area under the curve. But you might think, oh, this is some, yeah, it's not this area. The area under the curve here is not 100% represented by the green area. But if your delta x is very small, if your delta x is very small, and the difference between the area on the curve and the green area will be very, very minute. Yeah, that's the beauty of integration. Your delta x could be very, very small. If your delta x is small, the area, uh, okay, if your delta x is very small, the area, some area of this, the sum area of this will equal to the area under the curve. Curve. That's the original idea of doing integration. Find the area under the curve, and when we slice this area by lots of small rectangular area, and then we add this small rectangular area together, we will find the area we want. Okay, and if the slice is very, very small, delta x approach to 0, the sum of this patch equal to the total area. Okay, that's the area. That's the definition, the original definition of integration. So we want to also we use this idea. Let's do the from the very original. Okay, we want to do the area. Okay, so let's do this. We want to do the f of xi times delta x, and we summation all of them. Okay, summation all of them. And okay, there's two problems. What's the delta x and what's the xi? Okay, and our function is s squared. Don't forget it. Okay, what is delta x? Okay, and with the range we want to calculate is between 1 and 2. So the delta x, suppose, so we can slice this, we can do this. Our delta x is equal to the range, okay, range 2 minus 1, and divided by n, and n is approaching to infinity. That's why we say our delta x, we have very, very lots of small delta x, so that means our n is very large. And so what is xi? And the other problem is, what is xi? And here we use the right end because our range is between 1 and 2. 1 and 2. So suppose we have delta x. So okay, so suppose we have delta x. So our delta x, so our xi will be 1 plus n 1 over n, and 1 plus 2 over n, and 1 plus 3 over n, and all the way to 2. Okay, can you understand this idea? You understand this idea? Yeah, we have we slice with our delta x is 2 minus 1 over n, and n is a very huge number. So the delta x between 1 and 2, so our xi will be 1 plus 1 over n. So actually I would say our delta x is 1 over n. Okay, we have the 1 1 plus 1 over n, and 1 plus 2 over n, 1 plus 3 over n, and all the way to the 2. So we can write down this. So we can use our xi would be 1 plus I over n. Okay, I is our index, so our xi will be 1 plus I over n. And you might say, okay, and we start from, and I start from 1. I start from 1. I start from 1. Start from 1. Okay, and we do this summation. We use the right end point. So we start from the right end point. So we start from 1 plus 1 over n. We start from here. We start from here and all the way to the 2. Okay, this is starting point. Okay, we start from I equal to 1. Okay, so we have all the information, so let's do the calculation. Okay, we can lump this information together. So our area is equal to summation I, and f of xi, our function is x to the power 2. So xi is a1 plus 1 over I to the power 2 times 1 over n. And we have to be more clear of this, so we start from starting from 1, and 1 plus n to I plus n squared I squared and times 1 over n. So we keep continue to do the algebra work. Summation I and I. Okay, yes, we have the upper end, but where is the upper end? Upper end. We have a bottom end. Where's the upper end? Maybe we'll treat this later. So we have 1 over n plus n squared 2I plus n power 3 I squared. Okay, I think we are going to find the answer. Okay, so we use distribution law with summation I equal to E1 and 1 plus is n squared 2, because we are doing summation on I, so n and 2 is nothing to do with the summation, so we can factor it out. So equal to I equal to 1 I, and this is just do the same thing, 1 over 3 n to the power 3, and do a summation I was 1 to is I squared. Okay, so what is upper hand? I equal to e to infinity. So from 1 to, so our I should be infinity. Should be infinity. That's not true. Yeah, let me check my notes. Yeah, it should be upper end. It's n. Okay, it's n. Okay, it's n. Okay, oh, I got it. Okay, because we slide n points, so this should be your n. Okay. Okay, I almost forgot this. Okay. Okay, because we slice n, we divide, we have n patches, so this should be n. So I equal to from n. Yeah. If I is equal to n, this will be 2. Well, that's our end point. Okay, yes. Okay. Okay, so we are doing correct. Okay. Okay, so what's next? What's next? First of all, the first term you have because we are doing summation over I, so here, so n 1 over n can be factored out, and summation I equal to e, and this only 1 left, and 1 over n squared summation I equal to e1. Why do I write this over again? Okay, I squared. Okay, so this is a constant 1. So I'm doing summation from 1 to n. What's the answer? Remember that? This is n. Okay, and 1 n squared. So to do summation of I, 1 to summation I, and I from 1 to n. It's 1 plus 2 plus 3 plus 4 plus 5. Remember that? Okay, this is 1 plus 1 plus 1 plus 1 plus 1, and there are n 1. Okay, and this is a 1 plus 2 plus 3 plus 4 plus 5. Okay, do you remember the answer? And the final one is 1 square plus 2 square plus 3 square plus 4 square. Da, 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 da. Okay, remember the answer? Okay, you can check your high school. I think it's totally in high school. So this will be n times n plus 1. And this is, let me see, 6n times n plus 1 and times 2n plus 1. Is this correct? Okay, never mind. So let's do this calculation. So this cancel out. So this will be 1, and this is cancel out, and we have n squared plus n. So actually we have is some algebra work, but it's easy. It's 1 plus 1 over n. Oh yeah, you can factor it out. Okay, so the final one is a kind of complicated. Is n plus 1? Let me check. I'm gonna just make sure I'm doing. Yeah, I'm just make sure I'm doing everything right, and I'm afraid I'm doing wrong calculation. That happens a lot. So let me do a calculation here. So m squared plus m and 2n plus 1. So 2n power 3 plus n2 is 3n2, n2, 2n2, m plus n. Okay, so we'll have this 2 and 3 plus 3 and 2 plus n. Okay, so I think we are approaching to the answer. So it's 1 plus 1 plus 1 over m. So this will become 6 or 2 over 6 plus 1 over 2 and this is square. This is square, so this will be 1 and plus 1 over n squared. Okay, I think we reached the answer. And our n is approaching to infinity. Okay, n approaching to infinity. N is very close to infinity. N is a very large number. So our final answer is n plus 1. Because n is approaching infinity. So our answer is 2. Yeah, so answer is 1 plus 1 is 2 plus 1 over 3. So it's 7 over 3. Yeah, it's 7 over 3. Okay, that's our answer by using a very fundamental definition of integration. Okay, so it's 7 over 3. Let's check if we're using the integration rule. Is this the answer is the same? I'm not sure. I'm doing the calculation. Okay, so let's do this. Okay, checking the answer. So this will become 1 over 3 x3 and 1 over 2. So that would be 2, 3 minus 1 to the power 3. So it's 7 over 3. Okay, so use the integration rule, you will get the answer easily. And it is the same with using the original idea of integration. It should be the same. It should be the same. Okay, so actually when you do the integration, just using the integration rule to do the calculation. You don't have to prove this over again. Yeah. Okay, let's just show you. Even you use a fundamental calculation, it's equal to your user integration rule. Okay, so using integration rule because it's much easy to use and fast. Okay, so this proof just to convince you the integration rule is better better for usage. Okay, but you still have to understand where it comes from. Okay, actually it's very interesting calculation. Integration is very interesting. Okay, see you in another video. So I hope you can understand the origin of integration. I see you in another video. Okay, bye 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 bye.